Welcome all of you to the Incubation Academy. Today I am starting a new series of the simple harmonic motions numerical. A particle is executing simple harmonic motion of amplitude capital A along the x-axis about x equal to 0. When its potential energy equals to the kinetic energy, the position of the particle will be. Four options are given: A by 2, A by 2 root 2 and A by root 2. Before that, we try to understand what the kinetic energy and potential energy of a particle is. Let us consider this body is at x equal to 0 and it is at the mean position or equilibrium position. If it is in the mean position and at the equilibrium position, then we cannot say that forces are not acting on it. We can consider when this body is at x equal to 0, we can consider it is under the action of the two invisible strings. The upper string pulls it by the tension force capital T. Similarly, lower strings pulls it by the tension force capital T. So, under the action of the two equal and opposite forces, it is at rest, or the resultant force acting on it is 0. If I consider external force is acting on it from left to right, then under the action of the external force capital T and this capital T, a consequential force or resultant force generates, and that is in that direction. So this body is moving in that direction. So from the position x equal to 0, it now is at the position x equal to x. If it is at the position x equal to x, obviously these invisible strings are stretched, we can say. The tension forces are in that direction. With respect to that of the line of action of the force, we can say it makes an angle theta. So the two components of this tension force for this capital T, we can say this is T sin theta and this is T cos theta. For this capital T, T sin theta is in that direction. Since T cos theta is in that direction, so we can say it is 2T cos theta. T sin theta and T sin theta completely cancels out. So it is under the action of the 2T cos theta only. Since it is at the x position, so if I consider it is displaced by an amount x, and if the string is of length capital L, if I consider this is capital L, then this length can be calculated by the Pythagoras theorem, that is root over of L square plus x square. So what is the force if I try to understand? It is 2 capital T. Cos theta means base divided by hypotenuse. This is x and this is hypotenuse. So I can say it is x divided by root over of x square plus capital L square. Now if I consider this deflection, x is very small compared to that of the length of the invisible strings. So I can approximate this expression as 2t into x divided by L. Since 2 is constant, t is a constant and L is a constant, so the force which wants to restore itself in that direction, we can say this is the F restoring. That force is only depends on x, and it is in the direction opposite to that of its motion and towards the negative x-axis. That's how we can say this F restoring is proportional to minus x. Sometimes it is written as F restoring equal to minus of kx, where k is a constant. So this particle, as it is stretched in that direction, as the value of x increases, the F restoring force increases. Now at that position x equal to capital A, which is called the maximum displacement position, at that particular position, the F restoring is equal to that of the F external. F restoring and F external are completely equal and they are in the direction opposite to each other. That's the resultant force acting on it is 0. So the particle will not further move in that direction. So I can say the velocity of it is 0. So here, since the force is just applied F external, since it is moving in that direction, the restoring force developed in the direction opposite to that of the motion. So the velocity increases and it becomes 0. That's why this position x equal to plus A is called the maximum displacement position. When this particle reaches at that position, this particle will be at momentarily rest there. After that, since the F restoring force is acting in that direction, now this particle starts moving in that direction. When it comes here, this F restoring force is 0, but due to inertia, kinetic inertia, the particle cannot stop or cannot be rest at that particular position. So it is moving in that direction, and due to this inertia, it just crosses the mean position and it reaches here. Here also the same thing happens like this. So again it returns back and it continues oscillating above this mean position. If I want to describe it, then the x versus t graph will be something like this. That is a sinusoidal function. So if I write down, then x is equal to a sine omega into t, where a is the amplitude, that is the maximum displacement from the mean position, omega is the angular displacement, and t is the time. Now if I calculate the velocity from here by differentiating it with respect to t, then ddt of x will be equal to ddt of a sine omega into t. So it becomes omega into a into cos into omega into t. So from here, if I put a square minus of x square, then it is not wrong. Cos omega t can be written as root over of 1 minus sin square omega t, and after that by simple calculation we get the expressions of the V. So if I calculate the value of the kinetic energy, then the kinetic energy will be 1 by 2 into m into V square. So it will be 1 by 2 into m into omega square into a square minus of x square. So this is the expression of the kinetic energy. Now if I want to calculate it for the potential energy, this potential energy is completely responsible for this restoring force. And if I just integrate it, then I can get half of k x square. And if I put the value of k, then it will be 1 by 2 into m into omega square x square. So the expression of the kinetic energy is 1 by 2 m omega square a square minus x square, and expressions of the potential energy is half of k x square equal to half of m omega square x square. If I just try to do that integration, then we can also do this potential energy. A restoring is proportional to minus x, so it can be just, if I just writing down this value, then it will be kx. If it is stretched up to a distance x, then it is 0 to x. K is taken common. If I just do the integration on x, then obviously it will become small k into x square divided by 2. and this k, which is a constant, can be written as m omega square. So it is m omega square x square, as omega is related to k by this relation. So we get this is the expressions of the kinetic energy and this is the expressions of the potential energy.
So we have obtained that the position of a particle is x equal to s sin omega t, where a is the amplitude and omega is the angular frequency of the particle. Kinetic energy of the particle having the SHM is equal to half of m v square, and the potential energy is half of m omega square x square. If we equate the kinetic energy with that of the potential energy, then 1 by 2 m omega square within bracket s square minus x square is equal to 1 by 2 m omega square x square. 1 by 2 m can be cancelled out from the both sides, so we am getting s square minus x square equal to x square. So after the calculation we are getting x equal to plus minus a divided by root 2. If I want to look at the graphs, then the graph is here. This is the energy versus displacement curve. The kinetic energy and the potential energy, both curves are shown here. Kinetic energy by the solid line, while the potential energy by the curved line. And here you can see the kinetic energy and potential energy curve intersect each other at the point capital P and capital Q, where the points, particular points where the kinetic energy and the potential energy are equal to each other. That is, we have obtained from x equal to plus minus a divided by root 2 is shown here. Thank you all of you. Like, share and subscribe.